Okay, we are going to talk about areas in the plane. So we found the area under a curve before, so we'll talk about that, kind of review that concept, and then now we're going to talk about areas maybe between a couple of curves. So let's review what we talked about before. Now in class we didn't talk about using some of this notation, so this is a good time to do this, but if I'm trying to find the area under the curve, we did Riemann sums and we did left rectangle approximations, right, midpoint, and so on, and we basically added up a certain number of rectangles. Well, if we want to make every rectangle have the same width, then we can just call that width delta x, and we can draw this little representative rectangle to kind of represent what they would all look like, rather than drawing a bunch of them. So that would be your width. And so if I wanted to talk about what the area is, I could say, okay, here's the width, delta x. And then we're going to multiply it by the height, which would be f of c. Except that we're going to have a lot of rectangles here. And so just to distinguish the different ones, like the first rectangle, the second, the third, the fourth, we can put a little k here as our little subscript. So we can just say that's the function value of C1 would be the height of the first rectangle, and so on, and then C2 and so on. And so in order to get the area under the curve, the approximate area under the curve, then we would want to sum up all of those rectangles up to a certain amount of rectangles up to n. So if we were to make them all even width, then we would simply take the width times the function value of each rectangle, and then we would add them all up. And that would give us an approximate area. So if we want a better one, so that's an approximate area, we have several rectangles and we keep drawing them. Well, if we want to have better area, then we want to have lots and lots and lots of rectangles, and we want to fill it in, and they're really skinny, which I can't make too skinny with this pen, but you'd want to have infinitely many rectangles, and then we would get the exact area. So we would want to take the limit as n goes to infinity, and that would give us an infinite number of rectangles, which would give us exactly the area underneath the curve. And so you can see that on your notes, that page, that was that formula, and then that became the integral from a to b of f of x dx. Your delta x becomes your dx, and then you have your function, and we integrate from a to b. And so we've been doing that for a while. So now we're going to talk about if we have a rectangle that, or an area between two different curves instead. So we're going to draw in here basically a little representative rectangle of the basically the distance between. I'm trying to get the area of the shaded part, so I'm just going to draw a rectangle right here that sort of represents the way we could do this. We could make a bunch of rectangles and add them all up, and that would give us an approximate area. So this rectangle right here could be moved around. I can kind of cheat on the smartboard here and move it around, so that rectangle could be anywhere. If it gets over here, it's just a little shorter. Well, maybe it's just a little shorter. Well, technical difficulties. I don't know why it won't make it smaller, but anyway, there would be your rectangle. We could move it around, and it would have, the heights would be different, but the width would be the same if I just left the width of that rectangle. And so basically then, the width of our rectangle, well, the width is going horizontally, so we would call it delta x, because the width is some little x increment, some little distance x. The height here would be, well, the height would be, here's my rectangle, so the height would be to go from the top of this rectangle down to the x-axis, but that would be all the way down, but the rectangle stops down here, so I would need to subtract the distance from the bottom of the rectangle down. Well, this first distance that I just drew, the one here that goes to the top of the rectangle, well, that's just the function value. This height is just f. And if I go to the bottom of the rectangle right here, this distance, well, that's on g right there. So that's going to be g. So the top of your rectangle is always going to be f, and that's going to go all the way down to the x-axis. And the bottom of the rectangle is going to be the bottom function down. And so my height then here in the middle would actually be then to take the top function f minus the bottom function g. And that's going to be how tall my rectangle is. So, and then the next question says, would the height and width be different if I drew it somewhere else? Well, no, because this is a function of f. We could even write f of x and g of x. And wherever I move it, it's still f is on top and g is on bottom, and it's still going to be f minus g for the height. And the width is just going to be still delta x. And so it's not going to matter if I move it around. Now, if I go to do the area between two curves, I want to sum up all those rectangles. Okay, so we would do the summation of those rectangles, k equals 1 to n, and you had your height, which was f of x minus g of x, which was the top one minus the bottom one, and then it would be multiplied by your delta x, which is your width. So you have your height of your rectangle, and here you have the width. And so, and then we just add them all up. Well, how could we get, that's not the actual area, but it's close. But if I add up all those rectangles, if I were to draw more in, we would see that there'd be some things that we would miss, just like we saw when we did Riemann sums. So let me just draw a couple in here, but you can see there'd be some spots that we would miss if we did our rectangles like this. And so we would want to get a better approximation by simply having more and more rectangles. So the more rectangles we have, then the better shape or the better the area is going to be. Well, so then if we go limit as n goes to infinity of this summation that we just drew, then we're going to end up with, and these will have to have k's here, I guess, which I guess I should have put up there because this is what's changing. It's going to be a different x value each time, and then times your delta x, and this is going to end up being the integral from a to b of f of x minus g of x, and then dx. So you're simply going to subtract the top one minus the bottom one here. So here it is kind of all written out. So this is what we were talking about. One thing that's super important is that you have functions that are continuous. And here we're saying that g is the one that is smaller than f. Those are just any letters that we want. So we're just saying in this picture, we're talking in this formula, then g was the one that was below f. And you're going to take then basically the integral top minus the bottom. Now sometimes your functions are in terms of y, and so the graph is kind of turned, and in that case you will do right minus left. And we're going to do an example of each so you can see how to do that. And it's not actually difficult at all. It's actually kind of easier to do it that way. Okay, so let's go through an example. So the hardest part, which isn't very difficult, but the hardest part is that you have to be able to draw these in order to find this area. On the AP test, these are the type of questions that obviously you would have to do without a calculator. And so you need to draw the region because we don't know, we have to know where to integrate from. We have to know what the A and the B are, and generally that's where things intersect somehow. So first thing we need to do, step number 1 here, is draw this graph. We're trying to find the region bounded by those 4 different equations. So we're going to draw a very quick but fairly decent graph. We want it to be pretty close to the actual graph. We don't have to get it rulers out and be all perfect, but we want a decent sketch. This isn't the time to run through it and just draw something. So we want to make a little bit of a decent sketch with some actual points and where they're supposed to go so that we can get an idea of this graph. So let's go with the first graph, y equals x squared plus 2. So this is a parabola that opens up, and it's going to have the vertex at 2. And then if you plug in 1 into x, you're going to get 3. And if you plug in -1, you're going to get 3 also, and so you're going to have a graph like this. The second graph is simply a line, y equals minus x. So that's just a line that goes through 0, 0 and has a slope of -1. So that's pretty simple to draw. Oh, I missed my points there a little bit, but that's pretty simple to draw. And then x equals 0 and x equals 1. Well, those are vertical lines. And so x equals 0 would be this graph right here, and x equals 1 would be right here. So what we've actually got here for our region is, this is what is bounded, where I'm drawing in green. So here's the boundary, and this is the region that we're trying to do. Now it's hard for me to lightly shade, so I'm just going to put kind of little lines, but that's the region that we're trying to do. So on your paper, you probably want to kind of shade that with your pencil. There's the region. Now we want to draw an arbitrary rectangle. It will make more sense to you as we go and as we do volumes why this rectangle is important. So you're going to draw it every time. So I'm going to draw what I call a representative rectangle. So you're going to put a rectangle here that shows where you're going from one piece to the other. So this part right here is my little representative rectangle. Now using that, we're going to set up an integral. So the fact that your rectangle is the horizontal is the width, then that's delta x. That tells me that this entire integral will be in terms of x. So that's why that rectangle is super important, and you'll see on the next example the difference. So if the width is x, the region goes from clearly 0 to 1, because I had vertical lines there that bounded it. And then I'm going to take the top function, which is x squared plus 2, minus the bottom function, which is minus x. And then since it's delta x, that becomes dx. And then there's my variable. Now, before I integrate, I like to go ahead and try to clean it up a little bit, like distribute your minus, and you can put them in order if you want. The main thing is add anything that could be added and stuff before you integrate it, to save yourself some work. So I'm just going to leave it in the same order it's in, but I'm going to get rid of the minus and negative. So I have x squared plus 2 plus x dx. And so now all I'm going to do is go through and actually just integrate it, and this should be something we know how to do very well. And evaluate it from 0 to 1. And so I'm just going to do that down here. So if I plug in 1, I get 1/3 plus 2 plus 1/2 minus parentheses. Plug in 0, well, you're going to get 0 plus 0 plus 0. They're all going to be 0. And then when you add all of that together, you're going to end up with 17/6. Be sure you practice your fractions there so you can add that. And that's the area between those two curves. So now let's do another one. Now notice this time that your graphs are x equals and x equals. Now even if the second one wasn't x equals, we could make it that way. The first one would be difficult to solve for y. You would have to do some two pieces and things like that. So it's actually much easier to probably leave it like this. So we're going to go ahead and draw a sketch. And this time our graph is going to be in terms of y. So if you're not sure what something looks like, then remember, a great thing to do is just make a little table and plot some points. So for this graph right here, if I'm not sure what it looks like, I can just make an XY chart. Difference is I would generally plug stuff in for x or for y instead of what I would normally do and get the answers for x, because it's solved kind of that way. So if I plugged in 0 for y, I would get 3 for x. If I plug in 1 for y, I get 2 for x. So let's start there. I have 3, 0, and I have 2, 1. Well, we should kind of be able to see then that this is actually a parabola turned on its side. If I do y equals 2, I'm going to get 3 minus 4, which is -1. So at -1, I'll be up at 2, and then you can see there should be a mirror image down here. So that gives me a pretty good graph. The other way to think about it is, it's just like graphing y equals 3 minus x squared, only it's just turned on its side. So it's going to open, instead of down, it opens left. So there's that graph. Now this line might be easier just to think of it as y equals x minus 1, because then we can just use the intercept and the slope. So crosses at -1, and then the slope is 1. So we're going to get a line just like this. So the region that I am trying to integrate is right here. Now, let's say we go just like we did on the last problem and we try to draw a rectangle with the width being horizontal. Well, if I draw a rectangle where here's a rectangle and there's no difference, it's the line minus the parabola. But what if I draw a rectangle over here? Is it the line minus the parabola anymore? No. Things are a little different. So this would not be the best direction to draw the rectangle, and that's part of why we draw it, so we can determine if that's the best choice. And in that case, it's not. If I draw a rectangle this direction, then no matter where I draw it, I am always going to get the parabola minus, I'm always going to have the parabola minus the line. You can see as I move it, it's still going to be the parabola on the right and the line on the left. So that rectangle works best. Well, since it's turned sideways, then the width of this rectangle is actually delta y. Okay, because the width is going in the y direction. So this tells me my entire integral will just be in terms of y. So when I integrate it, I need to go from the y value to the y value. So I have this y value right down here to this y value right there. There's your top and your bottom of the region. So that means I'm going to integrate from -2 to 1. Now you might want to verify that that's actually where they intersect. Since we drew carefully, we can see that that's the y values of these points. This point right here is 2, 1, and this point right here is -1, -2. So the y value goes from -2 to 1. Now instead of top minus bottom, you can also just kind of think of turning your head. And if you turn your head to the right, the top is the parabola and the bottom is the line. And we just think right minus left. So we're going to take parabola minus the line, and everything needs to stay in terms of y. And we determined that because the width of my little representative rectangle was delta y. And then, like I said, I would go ahead and simplify that a bit inside, so that you're not dealing with having to add things. So I have a 3 and I have a -1, so that makes 2. And then I have minus y squared and a minus y dy, because remember we need to distribute this minus here. And so then I would again just do my integration and plug in my -2 to 1. So you're going to end up with 2 times 1, which is 2, minus 1/3, minus 1/2, minus parentheses. 2 times -2 is -4, minus -8/3 minus 4/2. So as soon as you're plugging in a minus and you got a bunch of powers, I would take your time. You're going to want to do a couple of steps there, and then when you finish, you should end up with 9/2. So this little representative rectangle here is very important because it tells me what variable I'm going to use in the problem. And so then your functions would need to be solved in terms of that. That will become really important when we're doing volume, because that's going to tell us everything we need to know about setting it up. So there's your information on areas in the plane.